Should I start now? Okay. Okay. So, hello to everyone there. It's a nice pleasure to be here for this talk. And we will try to show you some results in a brief way or about our work with fitting. You know that data fitting is a very important point when one is willing to get important information from data. So this is the point. Okay, let's expect that this will work. Let's see. Okay, so we have essentially two possibilities when we have data and we go for a fitting. One approach is a model-free, where parameters involved in the functions that are used do not have a predefined physical significance. This works quite well for some cases which are very complex, where the model, if you want to have a physical model, may be quite complicated, or in cases where you want just a fingerprint identification of sample, things like that. Otherwise, usually one is willing to have a physical model with parameters that has a clear significance, because at the end, we use the technique to get some information about a given sample. So we will focus on this point. This is about the problem. Okay, so now assume that we have a model that we validated the model on our data. What means this? This means essentially that we can explain with our model the information we have collected with the machine. Essentially, there is no fitting here, just testing. We get information about the physical parameters from other techniques. It may happen that the sample we're measuring has never been studied before, and then we are forced, in principle, to measure or to get some information using other techniques. Why? Because in general, in this technique, which is model dependent, the functions which we are using to fit we are moving in a multidimensional space. That is extremely complex if we want to get all the parameters without any external information. At least for the validation of the model, we need some inputs from other techniques. So in this example, you see here in the left side, we decided this is a dispersion curve of DMPC, which are quite standard lipids, liposomes. And this is the dispersion we have measured. This was measured in the laboratory of Dermot Brogan many years ago by Carla Mellegrande. And you see here that we expected to find in these lipids, at least for sure, three dynamical processes. One, ordered fluctuations of the lipids, because this is a local reflection of fluctuation of the liposome sphere. This is something that can be observed using microscopy in gigant vesicles, and there are other techniques where we can get some information about that such fluctuations are there for sure. So we have to include a dynamical process for this. And then we have diffusion of the lipids in the membrane, which is also something that has been observed with many different techniques. And finally, we know that there are some fast motions that are internal, intramolecular motions, and we include that motions that are not dispersive in the time scale which we are looking at this system, okay? So this was somehow shown in many talks in the past, but again, here is a good introduction. As an example, we are using this liposome. So you see that when we add these three models, and after we check that there is not cross-correlation between them, that says that the correlation functions, the cross-correlation functions are really negligible. and we extract information about the corresponding physical parameters that are involved in this model from the literature, we get this red curve, okay? So there is no fitting here. But we can see here that the model is working quite nice, except for this frequency range. So now we assume that another mechanism should be present, but that it was not included here. And we found out that lipids, rotational diffusion of lipids was quite often observed and discussed in the literature. And in some cases, we could get a correlation time associated to this. When we added this contribution due to this rotational diffusion, we could see that the model explains the data. This is the word I would like to use. The model explains the data. There is no fitting, not even a suboptimal fitting. This is just testing, putting the parameters, you get information, then you touch a little bit, and you get a result. And what is important is that all these physical parameters can be only on a given range. It's not possible to have a diffusion that may take any value, because you may get a very nice verification of your model, but with senseless parameters, which is quite often, this often happens with fittings somehow. Anyway, so this is, once you get this point, then you say, okay, I have validated model. I know that I have a model with physical parameters that I get from the literature, or I measure with other techniques, and I can explain the data. So I want to advise, this is not about relaxometry in liposome. This is just an example. The talk is about fitting. Okay. So from this last example, we can say that the physical sound parameters are restricted within a range. This is somehow logic. How you get the range? Okay, you can, if you have a system like DMPC liposome, which is something that has been studied with a wide range of different experimental techniques, then you have a lot of information in the literature with different techniques, and then you have defined a range. If not, it is a problem indeed, because you have, unless you can measure many times in different systems, and then you can get also a range. Second point, testing the model does not necessarily require a fitting process. This is important. I remember when I was working with him many years ago, he insisted in this point quite a lot. He didn't trust at all on fittings. Okay? Today, we are getting really ambitious, and we want to fit, and in fact, it is possible to fit, but we have to care about some details, okay? Finally, getting values of the involved parameters from other techniques is crucial for the process of validation of the model, okay? And only after we have checked this point, we can go, or has sense to go into a fitting process. You know, the model explains the data, and it is doing it with parameters that have physical sense. And of course, NMR relaxometry is model dependent, and this is the problem we have. We need a model to connect our data with what is going on inside the sample. So now we assume we have a validated model. Let's go to fit. The first thing we have to do is to check if our fitting is giving us some logical results. Why? Because it is quite common in a multidimensional space fitting that you can get a very nice fitting, but the parameters you get are absurd or wrong, let's say, okay? So one possibility, which is not the best one, at least in my opinion, is to get analytical quality samples and strict preparation protocol for the sample in such a way that it can be reproduced anywhere using the same chemicals from the same providers you use it the first time. Plus, you need, I insist in this point, some information about the system from other techniques, okay? In such a way that you have an idea, at least on the important parameters you want to get from your experiment. For example, in this example of liposome, the parameters we want to get, the important information we are willing to get from field cycling NMR relaxometry are the bending elastic modulus of the membrane and the diffusion constant. Okay. The rest of the parameters, of course, if they are correct, much better. But if we get really good parameters from kappa, the bending modulus, and D, the diffusion constant, we are done. Which is the problem with this approach? Is too inefficient, is extremely cost in time, and also you have a cost in the samples because you have to prepare liposome samples, can be used for 2-3 days maximum. So you have to repeat the samples, reproduce samples, and measure. And maybe to have 2, 3, 4 profiles, you can get 1 or 2 profiles, maybe 3 profiles per day at maximum, sleeping just a little bit. Anyway, so this is one approach. The second approach is to, once you have some experimental data, a good quality experimental data, then you can generate from that data synthetic relaxation dispersion curve. And then you can add some synthetic noise. And the noise, you have to reproduce the noise that the machine is putting on the data. This can be done. I will not go into the details of this because there is a paper when you can look for that. The time is short. I go to the more important points here. So what we use to generate these synthetic curves are the validated model, or the model we have already validated before. Okay, this is much faster, and you can generate a lot of curves per day, and you can do a large quantity of fittings to test if the thing, we will see what is the thing, is working okay. Well, this is something I would like to advise you, something that I never thought in the past I would reach this point in my life. I always rejected the use of synthetic data. But at the end, I had to assume that it was used. So what means the quality of the retrieval parameter? Well, this is the point we tackle in this paper. This is a paper, recent paper, when we analyze in general, and we use the field cycling NMR relaxometry as an example. So let's go to that. Okay. So the main general features we observed during this work are, one, the consistency of the model itself does not guarantee the success. So, oops, so many think about validating the model, and now I am saying that the model itself is not enough. Okay, this is, unfortunately, this is the situation. The second point is that the quality of the experimental data, I mean, things that has to be with noise, the frequency range we measure, the data density, how many points per unit frequency, etc. The second is the math characteristics of the model function, which can change quite a lot from one model to other model in a different sample. So this is tricky. So the mathematical characteristic of the sample is an important feature. And the third point is the math optimizing engine we use. These three things are entangled in a perverse way. So the perverse word is correctly applied here, believe me. So obviously, if you have a multidimensional problem, like in the case of liposome, we have a 7-dimensional space, is playing against. This is you have a 2-dimensional space, okay, you can fit using practically any reasonable optimizing engine and it will work quite well. But as soon as you start to increase the dimensionality of the problem, starts to be a problem. But now let's go to a feature, specific feature in more detail. And it has to be with the dynamic range. It is from the beginning, if your function, your model function, changes a lot in a given frequency range, and is not moving too much in a different frequency range, and you measure, obviously, whether the function does not have something interesting, you cannot recover important information that has to be with part of the model that is effective, where the function is changing a lot. So it seems to be a play of work, but this example is very simple. Let's go first to a very easy example. This is the case of a nematic, a thermotropic nematic liquid crystal, and PAA is quite standard liquid crystal, nematic phase. And people First, Pincus in 1969, he proposed a model with a quite clear frequency dependence due to ordered director fluctuations of the mesophase. And then people suddenly, you see, immediately after the paper of Pincus, people started to try to observe this frequency dependence, but the frequency range was not the correct. This is not the slope they had to observe in a log-log plot. It was when NOAC arrived with the phase cycling and extended the measurements up to the kilohertz frequency region, where it was possible to observe clearly the order directed fluctuation influence on the relaxation, on dominance on the relaxation. So I want to say this is a very simple example, but it shows clearly that the correct frequency or the correct dynamic range of the experiment may be critical to see what you want to see. A second easy example is this picture. I like this example because there are many different nanoparticles of different sizes, different forms, or geometric geometries, and supporting fluids. And you see the phase cycling is going up to 10 megahertz in this case. So forget if you want to see where's this peak, if you measure only until 110 megahertz. Here, for example, you can say nothing here. Where's the peak? It's not perfectly determined. Maybe if you fit there, you will get a result. Or here, or here, or here, even worse. So the authors here had to complete the range, extend to higher frequencies in this case, to get the information they need to get a good result. Okay, they did it with an electromagnet where they could change the magnetic field by changing it for the current, etc. So these two examples are very simple. Now, let's go to a less simple example. We come back to the liposome, 7-dimensional space. So what we see here is an experimental relaxation dispersion curve that was measured using a stellar machine. And we see the different processes that are involved in our model. Diffusion, or the fluctuation of the lipids. Now we replace it here, it's not rotation. Now we interpret that is in general, we call it intramolecular motion. And the fast motions that are also intramolecular. Here in the picture, we can see fast motion are present in some vibrations of connecting different atoms, part of the molecule, while the slower intramolecular motions mean some fluctuation of the chains and etc. So of course there are some rotations also involved there. So now we fix kappa and D, and we just take them from other experimental techniques. For example, neutron spin echo for kappa and diffusion, NMR diffusion from physics, just to ensure a good fitting. And then we get these parameters from this, which we will call the generator. These are the parameters with which we will generate the artificial curve for this case, the MPC 303 Kelvin, okay? And here we use the pattern search fitting engine, okay? We will see later some details about it. Okay, the point is here that you can get also a very nice fit without fixing kappa and D. You can use another fitting engines and you will get a very nice fitting, but the meaning of these parameters may be completely wrong or assumed. This is the model. It was shown many times in the past in different talks, so just to have a look, the order fluctuations, here the amplitude of different spectral density, the relevant parameters, the interproton distance, and this is the diffusion model is coming from Berkeley-Hals in a limit, and here is from where we get the diffusion constant, and here is from where we get the elastic bending modulus, and these are, here is R because it's taken from an old paper, but now we call this Lorentzian intramolecular match. Okay, so what we see here is the synthetic curve without noise. So it's practically in the difference with the original one are really, we can distinguish this one because it has no noise, and then we have the noise, okay? And if we compare the real curve that was measured with the synthetic, you see that there is no difference. And then we can produce many producing synthetic curves to analyze how the fitting engine is working. So this was a very important point in this work, to allow to produce a large quantity of synthetic curves from different samples and to test the fitting engine. Okay, not everything is perfect. This is the noiseless synthetic DMPC curve. We use fitting here with the generators, are those we get from the experimental first. And this is what we get from the PS fitting of the curve without noise. And then we can observe that here for diffusion, the relative error is much bigger than for the rest. By the way, we can see that here there is no restriction in this fitting. So we get the fitting without fixing nothing. And we see that we get a very nice result of the bending elastic model, okay? And the error is really small. And the diffusion constant is more or less okay, but it has a higher error. And also the amplitude. This suggests that something is going there with the diffusion that one has to analyze better. When we go to the noise, we add noise and we fit again. When we compare here, when we allow all the parameters to be free, that is, we do not fix nothing, no parameter fixed, all are free, we recover very good, quite good, the bending elastic module, but the diffusion is going to the box edge, to the limit of the range. Okay, and also again, we see that there is a difference in the amplitude. The rest of the parameters are reasonable, quite well, I should say. So again, this put a red light on the diffusion term. So now, if we compare, if we have two fittings, here we fix the constant, the diffusion constant, and here is free. Okay. And we see that there is a 1 order of magnitude of difference between them. So if we go to this low frequency range where diffusion seems to be that influence more the fitting model curve, if we amplify this, we see that they are completely undistinguishable. So 1 order of magnitude indeed changed nothing in the model here in this range. Okay. In addition, this is the range where the experimental errors are larger. So I come back here, and we see that the only region where we can just fish a little bit of information from the diffusion process is from these few points here. In the rest of the frequency range, diffusion is going far away from the data very fast. So this suggests that the problem with diffusion is coming from this, that we have a very low possibility to get information, a very few information, in a region where the error data, experimental error, are maximum. And then, okay, we can observe the following. This is only the diffusion model. Okay, this is the data we have collected experimentally. Now, for the synthetic data, so the synthetic data was not. So we see that the diffusion, all the frequency range where we have measured, shows no difference when the diffusion constant is changing by 1 order of magnitude. But if we would be able to extend the experiment to lower frequencies, then we will see a difference. This is only the diffusional model, and here is when we include all the model, the complete model. But we know that this difference, it comes from the diffusion. This is only changing diffusion. So this is the region of comfort we have. And we will see that even in this region, of course, we can get information. But in this case, it's tricky, you see. So this suggests that we have to extend the frequency range of the experiment to lower. Okay, we can do it easily using the synthetic tool once we have a model. We have a lot of experience of many years with liquid crystals, and we know that effectively this is going to a plateau. So these membranes in the liposome are lyotropic liquid crystals. It's not an exception. So we can trust that the model is approximately reproducing also the behavior of lower fields. This is a region where, well, one has to compensate the external magnetic field if we have an important field around the machine. It's tricky, but this is just for testing the fitting engine here, synthetic data, and we assume that all this data, simulating experimental data, are okay. Well, so now we fit, you see, 11 different curves like this. We generated 11 different relaxation dispersion curves, and in only one case, this is going to the box edge of the diffusion is going to the box edge. That means that the engine is trying to look the solution outside the interval, the interval where the diffusion constant should be. Okay, but if we measure up to 30 kilohertz, we will have many of them that will fail. Okay. So this example shows what's going on with 30 kilohertz and what's going on if we measure up to 1 kilohertz. Everything is simulated here, but I guess that this will be more or less the same when we will be able to extend the experiment to such a low field. So you see that the relative error of the diffusion is decreasing in a noticeable way, okay? And also, you can see that the bending elastic module has, in principle, an advantage. You get a better result extending the frequency range. Here, there is an example where we can see that the contrary holds. So that means that in a lot of measurements, in many measurements, you may have one that can be good even if you measure a 30 kilohertz. But forget that you will get a good result if you measure only one dispersion curve. In this sample, this will not happen, okay? At least with the machinery we are using to extract the data. Well, so these are the average parameters. We pick up the 10 simulated dispersion where the diffusion is not failing, where the fitting is not failing and diffusion is always within range. Even when we measure up to 1 kilohertz, you see that still we have a persistence of the power. This comes from a coupling between D and acid, because these both are belonging to the diffusional term, and there is a coupling because these two parameters. And even if we extend the frequency range, we decouple much more than if we measure up to 30 kilohertz, but still there is a persistence of the coupling. And also, which is also a Lorentzian function, we have a small coupling with the intramolecular motion term here. So, but which is the very important point here, which is the main parameter here, the parameter we want to measure here, the main one, the bending elastic model. So we are really lucky because we can measure it with a really good, let's say, precision. But okay, it's not a direct measurement, no, it's quite indirect. But it's not invasive. This is the main advantage of psilocybin. You have just supported, supporting fluid the liposomes, you don't do absolutely nothing to them. Magnetic fields are too low to produce a or some geometrical deformation on the liposome. So I should say this quite non-invasive technique, contrasted to other techniques that are quite invasive. So the fact that we can get kappa with less than 10% is a really good result. And now what we do with it? Okay, we have two possibilities. One, we measure diffusion with NMR technique to measure diffusion, gradient, Parse gradient or whatever, and we get the diffusion constant, we put it here, and then we can get, including kappa will be in principle better, determined, or we just are happy with this result. We get a result of the diffusion constant that is at least not so far from the generator. We have an approximate idea of how much the diffusion or how big the diffusion. Okay. Here, look, I am comparing different engine fitting engines, and I want to show you the detail. Well, here, this is for kappa, how we structure kappa in different fittings using different fitting engines. But we use Presentor, level marquard, and TRF, thrust region reflective. What is this? Well, this is a modification of level marquard in order to add box constraint for a parameter. You know that level marquard has no restriction on the range of the parameter. You can put range if you want, but the method do not need it. But if you want to add the box, then you have a version that considers it. The problem is that it's not a derivative free. None of them are derivative free. And this is important point. PS is derivative free. So when you have a function, your function has a complex derivative, this will be a big problem when you fit. That's why derivative free methods are very interesting, especially when you have a multidimensional space of high order, like this. Okay, so you see here, these are the seeds, different seeds. And the difference between 1, 2, 3, 4, 5 is the distance of the seed from the solution. So 1 is close to the solution, and 5 is far from the solution. And you see that the PS method is working quite well in the sense that not only reproduces the value of kappa quite well, but also is independent of the seed. This is an extremely important point. And Belén will talk about a little bit the difference of a global solution or a local solution. But if you have a local solution with different seeds, always the problem is you have a convergence to the same point, then you can assume that you have a global solution. If you compare with Lebeban Marquardt, open red circle, it also works quite well as far as you are close to the solution, and then start to fail. TRF is more or less working the same way here for these seeds, but it's not very precise in reproducing the lab. And these random are other 5 seeds that are completely randomly chosen. Of course, the same randomly seeds are used for these 2 engines, and you see that they are not working too fine. So I come back to TRF without with the same seeds. You see that it's relatively close, but when you start to use random seeds, which may be far away from the solution, it is failing. It's failing. Okay, and then we can do the same for diffusion. Here we see that we have a problem, in fact, with diffusion, because even the pattern search, while independent of the seed, is not reproducing quite well the value of the generator. And I come back to this point. Here there is not PS with random, because PS with random works exactly in the same. It is given practically the same solution. Okay, and you see here the differences on how level Marquardt is reproducing somehow when it's not so far from the solution, the PS result, and then start to fail, and also the TRF. Okay. You see the TRF here only works here and starts to fade afterward. Anyway, so this shows that essentially pattern search as a derivative-free mechanism is working quite well in the sense that independent of the seed, at least for this case, this is not general. This is an example for our case, a 7-dimensional space, liposomes, etc. Probably in polymers with a different model, everything will be different. Okay, but what I would expect that will not be so different is the fact that if you have a multi-dimensional space of high dimensionality, the NPS will be much better than the other. Of course, there are many others fitting engine. You know? Okay, so now I leave Velu to go on with the next slides.
Okay, hello everyone. Can you hear me well? Yes, Esteban?
Yes, yes.
Yes, yes, we are here.
Okay,
We can
How
hear
are
you.
okay,
Yes,
okay,
yes,
thank you.
yes, 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 yes.
Okay, well, let's begin with something like very familiar. That is the Levenberg-Marquardt method. That is probably the most widely used algorithm for curve fitting. Well, as Esteban says, Levenberg-Marquardt has a couple of limitations. It uses, well, derivatives, which are not helpful when the model function is complicated. And it also does not naturally handle problems where parameters must stay within certain bounds. And well, to overcome this bound problem, as Esteban mentioned, we use an extension called the Trust Region Reflected method or TRF. Well, here I am showing 6 fifths of simulated curves and nodes has been added to make it look like an experimental dispersion profile. Well, I want to, here's the key that if we know the generating parameters, we can really test the performance of each method and compare the solution fairly. Okay, in the top row, you can see 3 solutions using Levenberg-Marquardt, and in the bottom row, the fits with TRF. And from right to the left, the seed is placed farther away from the true solution. Okay, when you can see that when the seed is close, both methods converge well, but as we move farther away, conversions get worse, and eventually the algorithm doesn't converge at all. Levenberg-Marquardt is completely free in the parameter space, so failures can lead to unreasonable parameters. But on the other hand, TRF is restricted by bounds, so even failures look somewhat reasonable. But, well, this is important. When the seed is closed, Levenberg-Marquardt can outperform the TRF because the nonlinear transformations made in TRF to adapt the solution hyperspace to a bounded one distort the problem slightly. You can see that in the previous slide that Esteban showed. And well, given the complexity of our model functional form, we couldn't rely on a gradient-based method like Levenberg-Marquardt or anything similar. So we turned to derivative-free methods. Well, first we implemented a global minimizer that is called DIRMIN, which is an adaptation of the well-known direct method. But unfortunately, DIRMIN failed to find a unique solution after 10 days of running on a computing cluster because it requires a large numbers of function evaluations and significant memory, which is scaled rapidly with the numbers of variables. And well, because the mean was impractically slow, we decided to try a local minimizer, which gave us excellent results. And this is the method that Esteban mentioned, that is the pattern search method. that is an adaptation of the directional method from the 60s. I will try to explain it briefly. And it's a pattern search is an intuitive way to find the minima of a function. We start in a point that is our seed on a grid, and we pick a step size. And we evaluate the function at points plus and minus the step in every dimension, that's to say, around the seed in the grid. And if a point improves the function value, that's to say, if we find a lower value of our objective function, we move there. And this becomes our new center. And then repeat. And we continue seeking better points as long as we find improvements. And when none of the neighbors decrease the function, well, the next slide, please, Esteban. We shrink the step size and we start again. And well, this method, pattern search, is agile, doesn't need derivatives, it handles noisy functions well, and can systematically explore complex hyperspaces. Basically, is powerful for problems where gradient-based methods can be used. And well, to finish, a key concept here, as Esteban also said, is globalization. A method is considered globalized if, even though it is local, starting from different seeds leads to the same minimum. Well, in practice, we don't always need the absolute global minimum. If local minimizers coincide, we achieve a kind of practical globalization. This is exactly what happened to us in using pattern search in our system. Of course, we also need to account for the noise and set tolerances carefully to guarantee convergence and robustness. Esteban?
Finished? Okay.
Yes.
So I think there is one point I want to let me come back to this one. And the point here is that the fact that you see a nice fitting here do not mean that you have reproduced the generator. Okay. Here, this is showing that as you go outside this, as the seed you use is gone outside the solution, you reach a point where directly fail. Okay, but it may happen also that even when the fitting works quite well, you do not reproduce quite well the generator. This is something like was shown in the previous picture. Okay. So I think that this was a brief summary of our work, and it's just a minute to tell, but it was 2 years, at least more than 2 years work. Thank you very much.
Thank you very much. Do we have questions? Because I have actually a lot of questions, but well, I should not start. Questions from the audience. John.
I can ask something. Esteban. Sorry, my mic was off. Now it's on. Esteban, Belen, thank you for the contribution. Aim of this workshop was to collect different experience from different area with different background. So some part of your presentation, I confess I cannot understand, Esteban, because of my background. Anyway, I don't know in the other audience if you have any question, but the point is to extract from all this good tips for people who is approaching fitting of this NMR data. I'm not familiar with the fitting model you are proposing, and so I would like just to do a little effort, Esteban, and to give suggestion and recommendation to anyone working in this area to fit decay data and NMR profile, both. Tomorrow afternoon, we will have a kind of debate on this. There will be people.
I know. I will try to connect.
And if you would be available to participate, would be great. So
what I can say from this is a coupling, a microphone coupling. So what I can say in answer to your point is that in low dimensionality, it's reasonable that the commonly used fitting engines will work quite well. Okay, we have tested this in other models, not only in diapason. For example, in liquid crystal, pneumatic liquid crystal. Okay. Can you hear? I don't hear you.
can you repeat which is the fitting engine you have tested and you say it's working well?
It is called pattern search. So it works quite well when you have a dimensional space of several parameters, and when the function of the model you are using has a complex derivative. Okay.
I'm sorry, we have some technical mess here. The good results you get, Esteban, how much do you believe depends on the tool and how much depend on the preliminary knowledge you have on the system?
Okay, this is an important point. You should have okay. We can see the thing in two different ways, okay? Which is the use you will do of NMR relaxometry. Okay, we already talked about that. So if you are in the industry and you want to get a parameter and you need a good result for this parameter, you really need to make all this process I have somehow reflected here. You must validate your model. You should get data from other techniques. And then once you are sure that you can get from the data you have, with your model you have, and with the fitting engine you are using the results, then you can more or less use it in a standard way, and then you trust in the result. If you have a sample that nobody never measured, nothing, but you have only two parameters, the model is simple, then it's not a big problem. But in any case, you should have an idea of the range of the parameter. You must be able to detect a result that can be absurd. This is not so difficult. I mean, a diffusion constant. If you go from a liquid crystal to a membrane, and from there you go to other sample, similar sample, okay, you may have an expectation. But maybe you go to a completely different system, and you have absolutely no idea. And then, yes, if you cannot measure it, you can collaborate with someone measuring diffusion constant in that kind of system. I don't know, but it's tricky. If you want to get a fine result, then you should be very careful with that. Okay, and this is independent of the model of the fitting engine you will use.
Sure.
But
Something more,
Esteban.
You know that good results are also related to good experimental parameter. Okay.
Sure. Sure.
I mean, you have to set correctly all acquisition parameter related with the time window you want to explore, number of field, number of tau, and so on. did you make some preliminary, how to say, check about this set of parameters?
The machine.
Because we had this morning discussion on this, and we understood that it's very important to have how to say, a kind of calibration of the experiment in advance. And
Sure.
this is a trouble we have seen quite often happen, but just because the user is not setting properly the parameter. But setting properly parameters depend on the knowledge, I don't know, training and many other things of the user in the use of the machine, combined with some knowledge on the system they want to observe and what they are expecting. This is the story of the chicken and egg, but it's generating some bad
I completely agree.
things.
I completely agree with that.
So
This is
what do you
something that it
think
was.
about setting of parameter? Did you, your collaborator that have produced this data, are they familiar also on the critical and crucial parameter to acquire good data to be fitted correctly? So it's a strange question, but it's
Okay,
something
in my case, I can
that
answer
is
it very
often
very easy.
happen.
The first experiment, okay, the first experiment of when we started to collaborate with Dermot, they measured the first score, okay? So in that case, I have no control on the setup of the machine. But all the experiments we did, the first experiment, I did it myself and I set up the machine. And so we have a technician, a professional, let's say, that is reproducing these measurements, but he already knows which are the parameters.
Right.
And after that, we could reproduce somehow the measurements done in Dublin. So we could say that at the end, the setup of that original data was okay. Okay. But of course, this is an important point, very important point.
But sorry, Dermot is quite a skilled user. So in general, people are not of this level of knowledge. So I'm wondering if you are following some protocol to acquire good data, because probably
Okay,
if I
Johnny,
would run the
you know,
experiment, maybe I will not do as good
Johnny,
as you are doing because you have experience in this.
Johnny,
So I'm thinking to normal users.
Normal user, I have an answer for that. You know, the cars today, you know that everything is controlled from the ECU, the computer of the car. Do you hear? Can you hear me? There is no
Yes.
sound. Okay. Again. Today, modern cars are controlled by an internal computer. And you have different driving styles, okay, that are pre-programmed in the ECU. Okay? So what you can do is for standard samples, you know that the machine is used in quite standard samples. I should say that 70, 80% of the machine is being used in quite standard samples, protein solutions, polymers, etc. So you can fix some set of parameters from the factory that you can get this for polymers. These are the suggested. This is, at least for someone that starts from zero, this would be useful. You understand the meaning?
Yes, but not. I agree with you that this would be necessary, but also it's not easy to do this in advance. We discussed this morning that at least we need first have a protocol to calibrate the instrument according your sample. I mean, minimum T1 component, the fastest T1 and the shortest T1, and then set the time window accordingly. And then use as many tau you want, just to catch the complete time window. But before
Johnny,
doing this,
I
it's
completely
important
understand.
to check other situation like signal to noise. In the middle of the NMRD profile, we know that we have low signal to noise. And this is crucial. Signal to noise, I believe, is driving anything here. So we are trying to make some kind of protocol recommendation. Nothing can be automatic, because what you have done is very much based on your experience, grown in years. So I'm not sure I could explain you exactly which is the issue. We want to make
But I understand completely, but this is a
use and
discussion we have
interpretation of
here.
this data to normal users. And
I
of
know, but
course,
it's
it's
not
necessary to do what you suggested, to prepare a
Johnny,
set of parameters depending on the, how to say, the system you want to observe. You need to prepare some basic parameter setup to make sure that you collect the signals at the best. So these things. And
Johnny, this is
because
something we have been discussing in the last
Esteban,
5 years.
what you and Belen have done take, how to say, is based on a lot of knowledge you have already.
Okay, but listen, what you have said is not only for beginner. The calibration of the machine is an important point for everyone. And the only way to do this is with this is what is standardly accepted in the metrological ambient, let's say, is with inter-laboratory experiment. Using exactly the same sample, you have to check that all the parameters of the machine are the correct, and you have to previously you have to know, you have to check some things in the machine that a standard user cannot do it. So this is tricky. Some points, just what they have access in the let's say in the computer. Okay, you can adjust everything, but maybe there are some parameters that are important, and a beginner will not have access to that. So anyway, it's not something simple. It's not something simple, but it's not impossible to try to do something in that way.
This is
No sound.
exactly what we want to do. Make things simpler and results more reliable, and I don't know. So improve the quality of data that people, even normal user, can get. Imran, there is some. Okay. Sorry, Esteban. My questions are not very clear. You can understand me.
No, it's okay.
We feel the
Yeah.
issue. We feel the issue, but I don't know exactly how to give the problem and describe the issue. Maybe tomorrow will be the best time to struggle this point.
Just hear some question. Yes, I have one question. I'm wondering.
You're muted.
Here I am mute, I know, but
There is another microphone.
there's another microphone here.
Okay.
Okay, so but anyway, repeating. You said something, in my opinion, which is very discouraging. Sorry to be so frank, but you demonstrated a kind of very nice fit of a data. Then you said that actually the fact that the fit is so nice and reproduces the data so well does not mean the fit is good. So being, how to say, you know, so I would say, no, okay, I put a lot of effort. I have a kind of equation. I fitted this model, yeah. I put effort to have some ideas about the parameters, so I do not arrive at conclusion that my mass is negative or something moves higher than the speed of light or something like that. So more or less the parameters which I got to my knowledge are not entirely stupid. And then still my fit is not good. So what, first, why it is not good? Second, how can I realize and recognize that fit is good or not? Yeah, so I will be very frustrated after this. And could you just comment on this? Why you think that your excellent fit is not good?
Well, this is the main problem here, because you may have, depending on the fitting engine you're using, you may have different local solutions, and all of them looks like a very nice fitting. But only one of those will be a real solution, or the best solution, let's say. I don't know if the global solution, but the best solution. If you're lucky, like in this example we have here, where independent of the seed, you always get the same result, then you can start to suspect that your solution is very close to the global solution, okay? But in any case, if you do not compare, if you have nothing to work, then it's a matter of faith. The only way, I'm sorry, but the only way to know that the parameter you get from field cycling is okay is that you measure that parameter with other technique and you get a similar result.
Well, sorry, I would not really entirely agree. I think that, well, if I just take one data set, one profile, and the profile does not have many characteristic features, what usually happens, I would be more worried, not about the accuracy of the fit, whether I find a kind of local minimum or global minimum, but rather of the model which I use. Because I suppose that, I have a curve which does not have many features. I can reproduce it in terms of, I don't know, superposition of Lorentzian function. I can, reproduce it in terms of power law functions. I can reproduce it in terms of many other functions. It's just a matter how many times I add and how many parameters I have. So I would think that the accuracy of the model, the physical accuracy, the logic of this model would worry me more than the fact that I can be in a kind of local minimum. Because if the model is okay, at least this is my experience, even I can relatively easily realize that I'm dealing with a set of parameters which is not the optimal one. Because, for instance, one performs experiments versus temperature. And there are some obvious things. As long as I do not have phase transitions, for instance, higher temperature means faster motion. So if I am not able to keep this trend, it means that, well, this is not the optimal fit, yeah? That I find a kind of local minimum. If, for instance, the structure of the sample did not change, yeah, molecules usually do not change structure. However, I'm not able to keep, for instance, parameters like dipolar relaxation constant, temperature independent. This means that I'm also losing the plot, yeah? So somehow here we have some control. If you look like in a broader way, we look for consistency of the analysis. I would still am of the opinion that selecting the right model is the step which creates the highest danger.
Okay, but we are speaking of two different things, Danuta. What I showed was somehow the way you have to do the first time. Once you validated your model, it's okay. If now I change the lipid, I will not reproduce all this history. I will fit, and I will get the elastic constant, and I will transform it. Okay? So you have many models, for example, Fiteya or Rex or other tools around. They have incorporated different models that have been tested for a long time. Okay? So it's okay once you have tested the sample that this model is working perfectly with the sample you have, etc. Of course, you can use it. And this is the essential point of this school, I think, is because the machine, this is something I told to Gianni days ago. The machine has reached a state of maturity from the instrumental point of view, which is very high. So improving the machine, of course, it is always possible, but this is already really good. So now, how you do to put the machine or give access to the machine to someone that is going just a beginner, entering into the technique. So you need some software that helps to interpret the data, okay? So once you have validated the models, and most of the models that are included in these tools are already validated from many years of work. And the other point, Danuta, it depends quite a lot on the dimensionality of the problem. If you have only 2, 3 variables, this is not a problem. Usually you will get a good fitting once. But again, you should know that the model is validated. This is an essential point for me. So it's logic.
Yes. Because for instance, I will put it in this way. You said that a lot of models is validated, yeah? Well, I mean, it depends what you mean by validation, because, well, I do not question the mathematic principles that, I don't know, Fourier transform of exponential function is Lorentzian, or something like this. But for instance, just going into mathematical properties, I can have several relaxation terms. Usually, actually, specifically for liquid crystals, I was arguing for a long time with Pedro about this. You have many components. Like you have, component for every single piece of the profile. And what is actually happening? I can reproduce, for instance, part of the curve using just power law. I can reproduce, very likely, also part of the curve, using a model for two-dimensional translation diffusion, because it also gives something similar to a power law, at least in a narrow range, and so on and so on. This is only one of very many examples. However, if I, for instance, and this was a kind of example which I analyzed recently, if, for instance, I stick with the model of two-dimensional diffusion, at a certain moment, I get diffusion coefficients which are nonsense. So somehow this is a kind of warning, and so on. So I do not know what you mean about validation of a model, because in this sense, models are never validated, because there is almost always a matter of debate what the system really does.
Well, this is the point. The models, before you start to use it systematically, should be validated. And the way to validate it, you have two different ways to do it, at least. So all the rest you say is mere speculative argument, sorry. But unless you validate the model with contrasting your model and the parameters you get with recycling with the results from other techniques, at least the more important parameters of the problem, or you generate synthetic data like we did, and you check that you can recover the generators, etc., etc., etc. It's difficult to say that you can trust the model. Anyway, I think that there are models that have been used many times where the results extracted from people from that models were consistently with other values reported in the literature using other techniques. And this was even not try to do that in that moment, okay? You know that the main problem from the laboratory of Stuttgart was that people never trust too much in these fitting processes with so many parameters, okay? Because it is a matter of discussion, of course. That's why the validation of the model is so important. But I am a little bit more optimistic than you, I think, that in some samples where you do not have such a big quantity of parameters.
Well, I do not think we have much time to discuss this subject, However, when you put it in this way, of course, there are situations when I can validate the model, because eventually I understood what you mean by validation, just obtaining some parameters and comparing with the values of this kind of parameters obtained by other methods. Of course, if you can, have independent source of information, results obtained in different ways should be consistent. But quite often you do not have independent source of information, because after all, NMR alexometry is quite unique. And the thing is that, if I perform, for instance, NMR alexometry experiment on ionic liquids in, I don't know, a kind of iono gel, I do not want just to get the diffusion coefficient, because after all, I could use field gradient. Yeah, what I want to get, I want, for instance, to confirm or prove or disprove that, for instance, the geometry of the gel provides a kind of geometrical restriction for the diffusion. So I want to access the dimensionality of the motion by applying specific model, and this is not information which I get by other methods. So it's somehow, if we have recipe from other methods for everything, we do not need a alexometry. And we still argue that this is quite a unique method. Yeah,
Oh, sorry,
if
but I agree,
I
partially
can get
agree.
all those quantities and all those information from other methods, why bother with NMR alexometry? If I have to use here some models, and in fact I never know, and things like diffusion coefficient I can just measure. And so on.
So, Danuta, there is one point that is not is important here. Everything depends on what is you willing to do. So if you do not have, in metrology, there is a very basic rule. If you do not have traceability, you cannot ensure that a parameter you measure has a given value. You should have traceability. Okay, if the only objective here is to publish a paper, then it's no problem. You measure, fit with any model, and then you publish. That's clearly that this works. It works. But if you are in the industry, suppose, and you need a field cycling, why you field cycling? Because you may have I don't know, a general view of the dynamics of the system, and probably if you are lucky, you can measure one or two parameters. But this is a deeper discussion. It's not for to solve it in 5 minutes.
Yeah, this is the discussion. But as we try to help people to perform experiments in the best way, yeah, avoiding mistakes. So this was the purpose of the discussion, just how to minimize the risk of, spending a lot of time and then getting parameters which do not look like being nonsense at the first sign. However, when you go deeper, they are not accurate, yeah? So it was about useful tips. So for instance, I don't know, from my side, I consider, as useful tip, saying whether how some parameters evolve in temperature and whether the evolution is logical and so on. Okay, he has enough.
Well, I want to say bye. I thank you for this invitation. Tomorrow I will try to join you for the discussion. I promise I will shut my but nah. So we see you again tomorrow. Okay? Don't block me.
Thank you. Thank you, Esteban.
Ciao.
See you tomorrow.
Ciao. Bye bye.
Okay. It seems that we moved to less controversial things, and we'll have lecture about something related to food, and Faisal will present data. And I don't know, maybe some attempts to analyze the data. Maybe this will be also a good opportunity to look at the quality of the data. Yeah, because this is what we keep all the time, and somehow we keep discussing this. So, well, as this is a kind of workshop, we could see what we have here.
So am I audible? Am I audible?
Faisal, we do not hear you.
I hear you. Try again.
So, may I audible? I am audible?
I still hear you. Let me check.
I hear you.
I can hear you.
Okay. And you are seeing my screen?
Yes.
Okay. And you can see the slides are also moving, right?
Yes.
Yes.
Okay. Okay. So that I am Faisal, and I am a PhD student of Professor Danuta Krug. Thank you so much, Professor Danuta, and thank you so much to the stellar team that they considered me to be a part of the presentation, to be a part of the workshop. And the topic of my presentation is molecular dynamics of lentil and fava bean proteins. They are basically legumes. They have been investigated by 1H NMR relaxometry. So basically, I want to tell you that why basically we used this topic, because this is I can say this is one of the part of our NMR Improve project to work on the dairy alternative. And one of the dairy alternative, one of the part of the dairy alternative is basically the plant proteins. And the plants are basically the rich source of proteins, and we select the legumes. And as we know that the legumes are rich source of protein, and mostly the legumes contains the most abundant proteins that are present in the legumes are basically the globulin and the albumins. So moving towards the objective of this presentation, maybe. So basically, the objective of doing this research is basically to understand or to examine the molecular organization of protein structures, the water mobility, and their dynamic behavior using fast field cycling NMR over a longer time scale and wider frequency range. The frequency range that we use in our lab, it goes from 10 kilohertz to 10 and 20 megahertz, but I made this sample from 10 kilohertz to 10 megahertz in reference to 1H NMR frequency. And if I precisely talk about this investigation, it's basically the investigating the mechanism of motion of water molecules in highly concentrated proteins that are basically present in the legume solutions. Basically, the legumes we have mixed the legume solution into the water to understand the water diffusion and the water properties and the water interactions. So the importance of this proposed study is basically the dynamical process in the protein solutions, and the solution is basically the highly diluted to understand the protein and the protein water interactions. And the next is the technique that basically we use is the fast field cycling NMR. So before going to the results, I would like to present the methodology and the principle behind the NMR relaxometry. So as already Professor Danuta discussed, and this basically, as you know, that the biomolecules and the water molecules, they include the hydrogen atoms. And the magnetic movements of this 1H nuclei, they can take place in an external magnetic field in basically the two orientations. As you can see in the picture, we have like the parallel orientation and the anti-parallel orientations to the field. And the orientations are basically, these orientations, they are basically associated with the energy. Or maybe in other words, we can say that there are two energy levels that are available for the 1H nuclei. And the energy levels that are basically available, they are populated according to the Boltzmann law. That is basically the lower energy level is more populated. And the most important is the polarization. And the polarization of any samples that basically stems from the magnetic field that changes. And basically, not the magnetic field, but from the difference, it basically stems from the, we can say the difference in the population, and it's basically proportional to the magnetic field. And when the value of the magnetic field changes, I mean, it increases or decreases, the population of the energy level changes accordingly until a new equilibrium reach, and that is basically is reached. And that at that time is basically called the relaxation time, the time it takes for the nuclear spins to reach to their thermal equilibrium state after being perturbed by radio frequency pulse. And this is basically the relaxation time. And this relaxation time is basically inversely proportional to the relaxation rate, and the relaxation and the time needed for the relaxation rate reflects the probability, or we can say the efficiency of the transitions between the energy levels. So that this relaxation time mostly depends upon the structure and the dynamics of the molecules. And then we have to analysis of the relaxation process in a large range of magnetic fields, because we have a large range of magnetic fields. And from that, it allows to obtain the information not only about the dynamics of water, but also the slow movement of large molecules. And the large molecules, the macromolecules, we can say the protein. So this is basically the backhind principle of this FFC NMR relaxometry. And from this principle, we are basically obtaining the information. So why legumes are important? I already discussed. Basically, they have the nutritional importance. So legumes, they're basically the lentils, beans, or the chickpeas. They are the rich source of protein, fiber, minerals, and the bioactive compounds. Maybe I can say the bioactive compounds. They are basically the phenolic compounds that have many antioxidant properties, and it is very essential for food security and sustainable nutrition. And if we talk about its functional importance, their water distribution, hydration, and its macromolecular structure, it basically affects the texture, cooking, quality, digestibility, and shelf life. And the scientific importance is understanding the molecular dynamics of water and macromolecules, because it is really important in helping in improving the processing method. The processing method includes the cooking, soaking, and drying, the optimization of the storage conditions, and designing plant-based protein foods. This is basically these are basically all of the reasons that we are shifting towards or mining the legume samples, legumes in FFC NMR. And why FFC is needed here, basically, like the big advantage of fast field cycling NMR, that it's basically non-destructive method. It measures relaxation without damaging the sample, and molecular level insight. It gives us the molecular level insight, detects water mobility, protein-water interactions, and also the phase transition. So, and the unique advantage of FFC NMR, it basically covers a wide frequency range from 10 kilohertz to 10 megahertz in overlap, maybe at 20 megahertz, and then allowing study of motions on different time scales. And then practical application can be used for quality control of legumes, predicting cooking behavior, texture, and industrial food processing properties. So these are basically of the practical application that we are using FFC NMR here. So coming towards the data analysis and the data we produced here. So we got we have made this legume sample from 10 kilohertz to 10 megahertz, but then we have an opportunity to work this to perform this experiment in the Professor Pedro's lab. Professor Pedro also made the samples. So we are in process. We are measuring the samples, but we just managed to measure one sample at higher magnetic field, at higher magnification, like at up to 300 megahertz. And we also made this fava 90B protein. So we have different kind of lentils and the fava bean proteins, and we made the relaxation properties of all of the samples at room temperature, and to see the molecular mobility and the water diffusion properties. So before going towards the data analysis and before going towards applying the model, we just collected the fingerprint that which model is basically most interested and more good to apply. So we applied this. We take the the natural log of the frequency, and we see the linearity. And I show you the linearity of the one sample. As you see that it is a linear. So we decided to apply basically this two-dimensional motion, because when we apply this logarithmic model, you can see that we have the linear motion in it, and then we apply this two-dimensional model to understand the isotropic motion of our samples. And then we combine this two-dimensional 2D model with the power law. And then because this power law basically describes, and we have also applied this, we combine the two-dimensional translational motion with the power law, and this power law describes the dispersion of the relaxation rate with frequency. And in the power law, we have the power law exponent, and this power law exponent describes how strongly our relaxation rate depends on the frequency. And as we have large value or large number of this power law exponent value, that means that we have more complexity and more heterogeneity in the samples. And in our case, for example, if we particularly talk in our samples, in our legumes, so power law exponent, we try to apply the power law, and it's basically trying to get the information about the distribution of the correlation time and the complexity of water, and also the heterogeneity of the legume samples, that among them how they are basically we can say that how they're basically differentiated, and how much they have the capacity to hold the water and to hold the protein. So we made 5 different kind of lentil samples, and one of the fava bean 90C we made up to 300 megahertz in Professor Petro's lab. But in 2 cases, as we see here, in 2 cases, fava bean 90B and 90C, as you see that we have a whole value of this majority. The motion we have, this is the basically we have the power law, we have the heterogeneity, it has more power to hold the water. So that's why that was the reason to apply the power law and to understand the 2-dimensional or the translational diffusion. But at the other samples, like the green lentils, red lentils, and the yellow lentils, you are also seeing the 2D translational diffusion motion and also the power law values. So when we apply this model, we get this kind of values, and you can see here, and you can see here in table 1 and table 2, we got this the values of power law and also the 2D translational diffusion. So here I already said that the power law is basically depends on how our relaxation rate is dependent on the frequency, how strongly it depends on the frequency. So the green lentils, and from this table we can say that the green lentils, they show the faster molecular motion compared to red and yellow lentils, and the red lentils, they exhibit an additional restricted motion, which suggests us about the structural differences, more complex, maybe we can say the more complex water molecule interactions. And then we have the amplitude value. We can see here the amplitude is much high, as you see here in the yellow lentil samples. We have the high amplitude, and this suggests the higher solid or macromolecular fraction. And then we have the values of alpha that basically show that the lentil, if we can differentiate about all of these lentils, we can say that the yellow lentils have slightly higher heterogeneity compared to the red samples, because you can see the value of the alpha of the yellow lentil, it is higher. And then also, we can say that the important concept is about the water holding capacity of the legumes, that how much they have the ability or the capability to hold the water or to hold the protein. So this is the part of the study that I did with the help of Hochschule Weinstefan-Trasdorf University in Germany. But this study is still continued, and now we are basically at the stage of mining the samples to, like, we are going to pasteurize the sample, and after pasteurizing the sample, we want to make the sample again to see the differences before pasteurization and after pasteurization. So I'm thankful to this Weinstefan-Trasdorf University, also the Stellar, that gives me the opportunity to talk about some of the part of my research, and also the NMR Improve. If you have, so this is the end of my presentation. If you have any kind of questions, I'm ready to answer and discuss.
Well, I have to say that I almost forgot about the analysis. I remember we were analyzing the data some time ago. So the question was why you didn't write a paper about it yet. Yeah, but putting this question aside, although not forgetting it, other questions are welcome.
We decided to make that pasteurization part of the sample. So maybe, but I'm ready. I already did the introduction part, material method part.
Yeah. Do not try. I mean, it was a direct question. This week is last time.
But yeah, we have to write
scientific questions.
Yeah.
Well, I can only comment that here is a kind of example, that I do not know whether other model makes sense. The only criterion was somehow the simplicity of this description. Because after all, if I look at this figure ABC, there seems there's some mistake in the labeling. It should be DEF later, but whatever. This DEF can be somewhat problematic, but if I look just at ABC, I just see that, this is nothing else like a power law. End of story.
Yes, exactly.
So whatever, of course, I could also reproduce the data using, I don't know, combination of Lorentzian functions, because one can do this always. But I would propose first to look for the simplest solutions.
Okay.
So, Professor, maybe I can add a
Yeah.
question. It's not a question, but just comment and suggestion from you, Dilip, because as we are discussing, the focus of the workshop is to give, I would say, let's say, basic user or user new in the NMR community, a tool which could make their like a working life easier instead of increasing complexity. So since you are using of FFC instruments and also other kind of instruments using different algorithms, and I also saw one of your previous presentations where you shared your research about dairy products. They were, I think, maybe cheese or milk based, but I don't know what. But they were one of in your second you shared this. So my question is, during your experience with in NMR, in FFC NMR, what kind of issues you are facing, and what you think can be improved for from just your point of view to make things easier for you in future, just like the comments or suggestion which you want to give us so that we can make things easy for you and others like you who are in this NMR improve group who are doing their research in this field.
Well, thank you so much. I would really like to comment because obviously initially it is like the software is not initially the software was not user friendly, but then when one has to work, and then and now we know how to perform this all of this experiments, but uh, the, the main difficulty we were facing about doing, and when we were basically made in the magnetization or yeah. So basically when we perform an experiment and when we were able to perform the magnetization, but we were not whole like the whole value, like the whole curve, like not maybe the end of the curve we are missing or start of the curve we are missing. Maybe we can increase, and also we also think that there is a limitation that maybe we cannot increase the tau value, or maybe yeah, the RD value more than 3 or more no, because we always used to have the tau values not more than 3 because of the safety of our equipment.
This was something which I was there. I like I was told that this is what we can't do, but no, it's not like that. I think this is something kind of a misconception which is there. Otherwise, based on instrument, I know you can use more than that. So I think these are few things which I was there, we discussed. So probably now they know that it's not like.
Yeah, but I want to ask if we increase that value, obviously it will increase the time. It will increase the time of our sample. But if we increase the value, do they really matter in all of the in measuring the curve or in measuring the like because I know that if we increase the number of scans, we have a like good like we have a beautiful curve, we can say like that.
Yeah, actually, yeah, these are things which with practice becomes a little bit more easy to understand. Yeah, but increasing scan is important when you have a sample which is not producing good signal, to improve the signal to noise ratio. In that case, scan is important, and we
Yeah.
suggest to our, let's say, users, try to do at least 4 scans with proper phase cycling, something like that, so that you can have a good signal to noise ratio. And I know for some samples maybe it's not that possible, but this is something which we suggest to all users, that do at least 4 scans. And other about tau and this, and so these are
Okay.
things as we discussed in the morning. I think you were hearing us that first we have to start with a sample and try to
Yeah.
optimize all the parameters, checking, doing measurements, increasing, decreasing different attenuation parameters, just to see what is the maximum value of these parameters, or the minimum value we have to use to get the maximum signal. And after that, we start playing with tau, all other things. Yeah.
Yeah, we will try to do this.
Yeah. So yeah, that's why we wanted to know, like, from your point of view, what are things. So I think there are a few things which we have to let's say improve from software point of view. Then there are few things which maybe as a user we need to know what we want to do. So I think it has to be from both sides to get to a good point.
Yeah, yeah. No, it's really important. We are very, very thankful to you.
Yeah. Okay. Thank you. I think I don't have any other questions. If someone else wants to say something or ask something, they can raise their hand if they are online.
I have a short presentation about cheese from Brazil toys with us here. So see you in 1 hour.
Bye.